We are in week 3, and in week 3 we're going to take a look at some discrete probability distributions. In total, we're going to take a look at 3 probability distributions. All 3 of these probability distributions are discrete probability distributions. So we are going to cover sections 3.3, 3.4, and 3.5. Now, we're going to leave the theory behind all of these probability distribution functions, including the derivation of the mean or expected value of the random variable and the standard deviation or the variance of it. In other words, we're going to have formulas we're going to work with directly. And for all 3 distributions, geometric, binomial, and Poisson, we're going to look at the general form of the distribution. And I actually may, for a couple of them anyway, at least for Poisson and geometric, do examples using a calculator by hand. But ultimately what we would like to do is we would like to get everything done in Minitab. Okay, so whatever we do in this video, we're going to do ultimately again in Minitab. So let's begin with section 3.3, geometric probability distribution. Let me correct my typo here. Probability. There you go. So we're going to take a look at this distribution. Now, the geometric probability distribution gives you the distribution for a number of trials until we actually observe the first success. Okay. Now, these trials, remember, a trial is repetition of an experiment. So these trials are Bernoulli trials. So what we mean by Bernoulli means there are only 2 possible outcomes in these trials, which then they can be classified as success or failure. The 0-1 kind of phenomenon. And it's named in honor of, the Bernoulli trial is actually named in honor of Jacob Bernoulli, the Swiss mathematician of 17th century. And here I have just a little interesting factoid. There's actually 7 brothers in the Bernoulli family. There are 7 members of this family: Jacob, Johann, Nicholas, 1, 2, and Daniel. Then there's Johann Bernoulli the second, Johann the third. So all 7 of them were mathematicians and statisticians, and all of them contributed quite a bit to the field of probability theory. Okay. Now the other thing is that we talk about outcomes being success or failures. A success may not have its usual connotation in what we do. So for example, a success could be the collapse of a bridge. That's not necessarily a good thing, right? Or a success could be the spread of a disease. In some instances, a success would be, for instance, if a small business goes out of a business. A success may be if an airline files for bankruptcy. So again, it's not necessarily a good thing. It could be a good thing. So the success would be, let's say, it would be that a company would thrive and they actually increase their earnings 30% next quarter. So whatever the success is defined. Now, so what is X? Again, X, we defined it earlier too when we defined the probability distribution. X is the total number of trials until the first success is observed. Now, if probability of success, we allow that to be P, then this would be the probability distribution of what we're looking at. Probability of X equals K. K here is a constant. Okay, X is a random variable. K is the value of the random variable. So probability of X equal to something is equal to 1 minus P to the K minus 1 power times P. Now the premise here is that, for instance, in order to look at success on the, let's say, kth trial, that's what K is here. So if I want to observe a success on kth trial, that means K minus 1 trials prior to that must have resulted in a failure, right? And because of independence of these trials, that's the other assumption here we have is independence of the trials, then we can actually write the probability in this form. Okay. Now note, by the way, the k here, okay, k actually can go to infinity. That means we may have to wait forever to observe a success. Okay. But it could occur in 1, 2, 3, and so on. Okay, and let's see. Actually, k here should be from 1, not from 0. Doesn't make sense to have it at 0. So please correct that. K is 1 that means success on the first trial. You cannot have 0th trial. Okay. So there we have that. Now the mean and deviation, standard deviation of random variable x are given by that. Now something about the mean here. Let's say, for example, if something has, if there is 1 in 3 chance of probability of observing a success on the kth trial, then the reciprocal 1 over 1/3 means 3. So you would expect to see the first success on the 3rd trial. If probability of success is 1/4, reciprocal of that would be 4. You would expect to see the first success in the 4th trial. Okay, so that's, just want to put that in perspective for you. Now here are some examples of a geometric experiments, or something that could lead to a geometric example of geometric random variables, I should say. Suppose we throw a dart at a bullseye, and we want to know what is the probability that you hit the bullseye on the 4th throw. Okay, on the 4th throw. Another example, let's say we're going to roll the die repeatedly, and the random variable x would be the number of times you have to roll until a 5 is observed. Let's say I want to know what is the probability that I observe a 5 on the 6th roll of a die, on the 2nd roll, on the 1st roll, 3rd, 4th, 5th, on the 20th roll of a die, and so on. And this one, where we actually now look at numerical example, and we will actually pursue this example by hand using the probability distribution, and we will go to Minitab, and actually I'll show you how to answer this question in Minitab. Okay, so here I made up a question. Suppose products produced by a machine has 2% defective rate. So okay, this is some machine that makes out pre-assembled parts. Okay, and 2% defective rate. We want to know what is the probability the first defective item occurs in the 7th item inspected. Okay, so 2% defective rate. I want to know what is probability that I observe the first defective item on the 7th inspection. Okay, so probability of success is 0.2, 1 minus that would be 0.98. Probability x equals 7 is what we want to know. So that means 0.98 is probability that there is no defective. Notice 7 minus 1 is 6. That means the first 6 must actually be not defective. So you multiply 0.98 by 0.98 by 0.98. And that the way that's done is due to independence of these trials, multiplying them, that is. And then we finally times that by 0.02, and if I did the calculations right, that number turns out to be 0.0177. Okay, so that's what that is. So in other words, about almost 2%, roughly 2%, a little less than 2% probability we observe the first defective item on the 7th inspection. What are the mean and variance? Remember, the mean is the reciprocal of the proportion. So if there 2% means 1 in 50. 1 in 50 probability of defective. That means you would expect to see the first defective on the 50th trial. Okay. And that's what this is, the expected number of trials until the first defective is observed, 50. The standard deviation, you go through the motions here and you get almost 50. That's just pure coincidence, by the way. And I call that the give or take. of the expected value. So I would expect, notice that's pretty large, by the way. Deviation relative to the mean is pretty large. That happens because p is so small. Okay. And here's actually how you can get that number that we got, the 0.0177. Oh, sorry, I didn't mean to erase that one. Let me put that back. 0177. I meant to highlight it. There. We had 0.0177. That's exactly what Minitab gives me. Now to the right in here, that's actually the probability distribution function, the histogram of it, if you will. Okay. That's the histogram. Notice how skewed that distribution is to the right. The center of the distribution, the expected value is 50, so I kind of have pinpoint where the 50 is. And that is the histogram, if you will. Now, as we go to Minitab, you will see you can actually hold the cursor over any bar, and it gives you the probability for that outcome. If I hold the mouse over it right now, it won't do any good because I'm in my notebook. But we'll see this in Minitab. And then I'll remind you of that. So there you go. This is a probability. Now, in part B, let's say I want to answer this probability question. I want to know what is probability the first success occurs between the 4th and 8th trial. Okay. Now notice 4 is exclusive, right? 4 is exclusive. It doesn't have equal sign. But 8 is inclusive. There's an equal sign on less than at 8. And in the case of a discrete, it makes a difference whether we include or exclude the value of the random variable, right? The outcome. So between 4 and 8, inclusive, 8 exclusive at 4, that translates into 5, 6, 7, and 8, right? So what is probability that it could be the success could occur? The first success could occur on the 5th trial, could occur on the 6th inspection, 7th inspection, or 8th inspection. Now these numbers, I got them all from Minitab, and I'll show you in a minute. You will see the Minitab output. So probability of 5, 6, 7, 8 is given by those numbers. You don't have to do this by hand either. You get it from Minitab. That probability is 0.716. Okay, so I defined an event and we found probability of events. Now, this is one way to do it, and the way I did it is using distribution function, right? That probability distribution function, and of course in Minitab. There is another way we can do this. Let me show you. And that's using what we call the cumulative distribution function. What the cumulative distribution function does is it does just that. The word cumulative means you accumulate probabilities as you go from 0 to 1 to 2. Okay, and so on. So to the right here, I have right over here. You see this? This is what CDF means. The cumulative distribution function always gives you probability that the random variable x is less than or equal to x. That's what makes it cumulative, less than or equal. So if I have, as I do in this example, probability of x less than or equal 8 means everything less than or equal to 8. That means 8, 7, 6, 5, 4, 3, 2, 1 minus probability less than or equal 4 means 4, 3, 2, 1. Now, notice by the way here, what I've done is I have translated the probability statement on the left into an equivalent cumulative distribution function. Well, here I have less than or equal 8. So there's less than or equal 8 minus. Now, probability of x greater than 4. If I don't include 4, that means 5, right? I have a graph here for you. And I'm right in here. So again, I want probability of 4 and 8, right? So this is actually the representation of that probability statement. Between 4 and 8, inclusive again at 8, exclusive of 4, means 5, 6, 7, 8. So I want to find these 4 probabilities, which we did up here. So I'm going to look at the CDF. I'm looking at everything below 8. Everything below 8 actually picks up these probabilities too, right? It's going to pick up these unwanted probabilities. That's everything that includes less than or equal 8. But I really don't need those, huh? I only want the highlighted probabilities, these. So what should I do? Well, we're going to subtract probability of less than or equal 4 from it. That's how I got this. If you draw this, what I have, something similar to this, it really helps you set up these probability statements. Otherwise, it's a little abstract. Still doable, but this really helps me out. So, what did I do next? Because I have the distribution here, I got this from Minitab. So I looked at probability of less than or equal to 8, and that is this probability right in here. That's less than or equal 8. And notice this much is extra, right? This is all the excess that I don't need. I only want these probabilities. So this is going to give me 0.1492. That's this probability, right, at x less than or equal 8, minus the unwanted portion. Now, you don't actually add these probabilities, right? Don't worry about those. Okay, don't even look at them, because that 077632 actually counts everything less than or equal 4. So what that 0776 actually, what this number has in it, it has these 4 numbers. If you add up those 4 numbers now, those will add up to 077632. Okay, so that's what that is, and that's how I got these numbers. Okay, so hopefully you follow that. Now, the question is, how do I run this in Minitab, correct? So let's go to Minitab, and actually we're going to do this now. So let me just jot it down that our probability of success here was 0.02, and we're looking at geometric. So we're going to replicate the output that you see here in Minitab. So this is a good time probably to pause this video and invoke the Minitab 19 and see if you can follow along with me. So I'm in Minitab now. I'm going to input a column of random variable x here. Okay, and then I'm going to go 1, 2, 3, 4. Now, you can actually continue on for as high as you like, because remember, for random variable x, the lowest number is 1, and it goes to infinity. So I'm going to go to 10. How's that? That's good enough. Now, instead of typing all the way to 10, here's a trick that would help you out. If you slowly move the mouse, don't left or right click. Okay, don't click anything. Just move the mouse over, and there you go. You see that plus changes to a different plus, right? As I move from left to right, there you go. This plus. Now left click once and hold and drag. So if you drag this, you see the numbers changing. There you go. See how you can copy all of these numbers down? I went all the way to 94. I didn't need to. In my output, in my note, actually I went to 10. But that's okay. So there you go. Here are the outcomes, if you will, the values of the random variable x. Now, we need to generate the probability distribution for a geometric distribution. So, in the second column, I'm going to put G for geometric, okay, and then colon, probability, capital X equal little x, okay. And then later on, when you reference this, it will be easy for you to remember. G is for geometric. I'm going to use B for binomial, later P for Poisson. And I'm going to go G. This is going to be reserved for my cumulative distribution function. That's probability of capital X less than or equal to little x. Now, remember, capital X is the random variable. It's a literal variable. Little x is a value of that. Little x, for example, could be 1, 2, 3, 4. But capital X is the number of total number of trials. In our case, how many times we have to, how many trials it takes until we observe the first defective item. Okay, now we want to generate these numbers. let me go here. So the way to do it is we go to Calc. Okay, and then we go to Probability Distributions. Slide over and go up here to Geometric. Okay, so this is going to calculate PDF, CDF, inverse CDF, which we will not do in this course. So this is all we want to do, just the other two. So I'm going to go Geometric, click. Now, right up here, you click on Probability, that radio button, Probability button. The event probability, that was 0.02. That's the probability of success. Now, we do have an input column here. The input column is column C1, right? So I'm going to left click once inside of that field. And notice up here, C1X appears. You can select it. If you double click, it will go into that area itself. And notice there are two other columns that we created that they show up. And the reason they show up now is because the cursor is in the next field, which says, okay, well, where do you want me to store these? Okay, the storage column. Well, I would like to, because these are individual probabilities for those outcomes, I would like to store them in C2, in there. Okay, and then hit OK. And there you go. You see all of these. Let me slide this up so you see a larger area of my spreadsheet. There you go. So probability of success on the first trial, 0.02. Right? Remember, that was probability of success. First trial, that means you haven't had a chance for failure. Probability of success on the second trial, that means you must have failed on the first trial. That's 0.98 times, and success on the second is 0.02. If you do 0.98 times 0.02, you get this one. Next one, to get success on the third trial, that means you must have failed for the first two, right? That's 0.98, 0.98. 0.98 squared, that is, times 0.02, and so on and so forth. So there you go. This is how I got those individual probabilities. Okay, and that's where I got my probability of 5, 6, 7, 8, and so on from here. Now let's do our cumulative distribution for less than or equal. So you're going to go into Calc, Probability Distribution. We're going to go to Geometric. And this time, see, just a moment ago we selected probability. We're going to deselect and select cumulative distribution function here, cumulative probability, and leave O2 the same. Our input column is that we're going to change our storage. This time I'm going to store them in less than or equal to, because these are cumulative. And we're good. Hit OK. And there you go. These are the cumulative items. So the probability of... Okay, so there you go. We have all of these cumulative probabilities. So for example, this probability of 0.0588, that's when you add probability of 3, 2, and 1. When you add these three numbers, you get that one. Probability, cumulative probability at 6 means probability of 6, 5, 4, 3, 2, 1. It's the sum of all the probabilities at or below this, all the way down to 1. Okay, so there we have that, the way I had it in my notebook. Now, how do we get actually the graph, the histogram of the probability distribution function? Well, one other thing, let's say we want to find probability of exactly 5. Let me go back to my notebook. I guess there was one where I had the output. Yeah, right in here. Let's say we want to find probability of exactly 7, right? That means what is probability of observing a defective on the 7th inspection, on the 7th trial? Okay, so let's get that one from Minitab, the way I have it here. So here's how you're going to do this. You're going to go to Calculate, Probability Distribution of Geometric, and we want probability. Now this time I'm going to see right in here, deselect that and select Input Constant. There. Constant is 7. Probability of success on the 7th trial. Keep probability of success at 0.2. Now here it has optional storage. I'm going to store this optional storage. You really don't need this, but let's say you want to use the result of this probability for some reason later on in a formula with something else, then you can actually name it here. Let me just call it I don't know, constant prob, something like that. Okay, that's going to be a constant for us that, let's say, later on you would want to use this, and then hit OK. And let's see. Okay, so because I created a constant, now look at this calculator, and it's right in here. You see that constant probability, whatever that number is under K1, my first constant. So I could use this in a formula. Like I said, you're not gonna need this feature, okay, but you can use that later on. That's why you would want to select that item. So let me rerun this one, probability, geometric, and see that optional storage, I don't need it. I'm going to delete that. So I want to find probability of success on the 7th trial. Okay. And there you go. You see, now it actually outputs it. And this is what I had. That's what I had put in my notebook. And that's how you do this. Last thing, and we are done with this distribution, is let's get a histogram. So you go to graph, go down to probability distribution plot, click on that, and you've seen this before. Remember, for normal distribution we did the same thing. I'm going to go view single, okay, and select geometric. Probability was 0.02, and okay. And then this is what I got for my distribution. Now you can slide this, but you still don't see the whole thing, right? If you left click once, it activates the graph. So now you can, let's say, do these other stuff that you would like. If you want to edit it, copy it, send it, and so on. But let's say you actually want to see this graph, double click on it, left click, double click, and it actually brings it outside of that output area. Now you actually see a better graph. And usually what I do is I take a picture of this using another what do you call it, another application I have. Let me show you. There you go. It's called snipping tool. So you can download this snipping tool. That's what I use to copy different charts, different portraits, different images, and insert it in my notebook. So you could do the same thing. And if you click outside of that, left or just exit out, there you go. That disappears. So this is about all we want to do with geometric distribution. So let me go back here, and we are done with just the geometric distribution. Okay, so next what we're going to do is we're going to look at the binomial probability distribution. So I'm going to pause this video, this lecture. You might want to do the same and just take a short break until we resume again. Okay, next let's take a look at the binomial probability distribution. This would be the second of our discrete probability distribution. So just a few minutes ago we talked about the geometric distribution. Now we're going to look at the binomial distribution. Now before we actually take a look at this distribution, which I have its formula down here, let me actually scroll down. Okay, before we actually take a look at the probability distribution for the binomial, let's talk about what is a binomial experiment in here. So this is what I call the signature of a binomial experiment. In a binomial experiment, there are n trials. These trials are identical and independent, just like it was with the case of geometric. Each trial has two possible outcomes. Again, remember the Bernoulli success failure, we had that in geometric. And probability of success is fixed, whatever that probability is, p, and remains fixed or constant as we move across the trials, okay, as we go from trial to trial. So if any experiment qualifies for all 4 of these, then we call that a binomial experiment. Now, suppose we have a binomial experiment and we're going to introduce the random variable x to be the number of successes in n trials. So the probability distribution of x now is given by this formula. Okay, now, again, don't worry, we're not going to do anything with this formula. It's just for you to look at it. We actually use Minitab to find these probabilities later on. But just to give you the components of this binomial distribution, what you see actually in here, this part, this part, as I have it, it looks at how many ways you can actually have a sequence of success failures. Okay, and this latter part of it, so that's what that part is. And then this other part of that expression, this portion, actually takes a look at the probability of a particular sequence of success and failures. Okay, so that's what those are. And this is how the formula is put together. Now, random variable x can assume values 0, 1, 2, all the way up to a number of trials. So for example, 0 means probability of no success at all. It means every one of these trials will result in a failure. Remember, success failure doesn't have its usual connotation. Or what's probability of 1 success or 2 successes, and what is the probability all trials result in a success? That's what this one is. Okay, so let's take a look at now this nx portion right in here. This is what we want to look at. Okay, the formula for nx, and the way we read this, by the way, is n choose x. That's how that is read. Okay, so they read this as n choose x. And it's like, why do they call it choose? What is exactly it is? What exactly it is we're choosing? Well, x turns out to be the number of subsets of size x from a group of size n. That's what that is. So as you will see in a moment, through an example, I'll explain that. Now the factorial notation here, that's what this exclamation symbol means. This means factorial. And what is a factorial? Well, every whole number, every natural number actually has a factorial. So for example, and here I have the general form n factorial. So n is a natural number. N factorial is the product of n, 1 less than that, 1 less, all the way down to 3 to 1. And 0 factorial by definition is 1. So for example, what is 4 factorial? 4, 3, 2, 1 equal 24. You actually multiply. What is 10 factorial? That would be 10, 9, 8, 7, ... all the way down to 1. Again, since we're not doing this by hand, we don't spend much time on this. Now, the mean and deviation and variance of a binomial is given by these formulas. And this is again for binomial only. It's not going to work with geometric. Okay, remember geometric had its own. And there you have it. Now, as far as independence of events, in this case, just want to point that out. The independence is guaranteed by or facilitated by the nature of experiments. So for example, if I roll a die 10 times, each time I'm rolling it, the outcomes are going to be independent of each other. Each time the result will be different. So independent is here done by the way the experiment is conducted. Or if I toss a coin 10 times, that experiment inherently produces independent outcomes. Or we can do this by conducting sampling with replacement. Now, sampling with replacement, remember, that's when you select a subject and then you put them back in the population, they have a chance to be selected again. And that guarantees the probability of selection does not change. Okay, and there you go. The independence guarantees that P, probability of success, remains constant or fixed from trial to trial. And here's an example of making a selection with or without replacement, how it can change or affect the probability. Suppose that there are 2 red balls and 8 other colors balls in a bag, and I'm going to choose one ball. I want to know what is the probability that it's a red ball on my first draw. Well, there are 2 red balls, favorable outcomes, 10 possible outcomes. The probability is 1/5. Pretty straightforward. Now, suppose sampling is done without replacement. So that means I have 1 ball out, potentially a red ball outside of the bag. Now there's only 1 ball left, 1 red ball left in the bag. And the total is now reduced by 1, which makes it 9 balls total. So probability of red on the second draw is going to be 1/9. And notice how these probabilities, see, they're not the same, right? These probabilities actually changed. So that's what we don't want to have. Binomial experiment assume that probability is going to be the same. So what if I change without replacement to with replacement? Well, if I replace it, probability of red ball on the first draw is 1/10. Since I replace it, put it back in the bag, again there are 2 red balls in the bag, so the probability is again 2/10 or 1/5. And the same as on the first draw. Okay. Now, in practice, we don't really do sampling with replacement. All samplings are done without replacement. And we have this overarching assumption, and this is really the assumption that we have, that the population is so large so that when we remove a few items from it, it's really not going to change that fixed probability of selection. Okay. Now, the rule of thumb is if the ratio of sample to population is less than 5%, you can actually assume independence. That ratio of sample to population is also written as little n less than 0.05 n. It's not in the form of a ratio. The ratio I'm talking about is this one, which is really the same as what's in here. If you multiply both sides by cap n, you get what's down below. Okay, so there you have it. And going forward, this will be our assumption, by the way. We always assume going forward that we either have sampling with replacement, or the population is so large that removing a few items don't matter. Now here I want to actually have an example. You like this one. Suppose 12% of the world population are vegetarian, and I'm going to choose a sample of size 30 without replacement. See that? So when I select someone, I'm not going to put him back in the population. Now, probability is 12% as you draw subjects in this case. So why is this? Why is probability still 12% as you draw subjects of size 30 from the general world population? Well, here you go. The current world population, this is as of May 11th. Actually, there is a site that actually shows all of these. I'm sure it's programmed. They don't actually go around the world and count people. But based on whatever the growth rate is, they've created these population clocks that run and give you real time, as real as they can get. So as of almost the time that I've done this lecture, the world population stood at about 7.8 billion, call it, right? We're looking at this number. Pretty close to 7.8 billion. So here's my population of 7.8 billion. 12% of that is going to be about 1 billion. Okay. Now, probability of choosing one person is 12%, according to the way the problem was stated in the beginning. Now, suppose I chose one person. The probability for the second person to be vegetarian now, because assuming first one was vegetarian, now there's one less vegetarian in the population, right? So what happens to the billion? Now it's 999,999,999. And the world population is now reduced by 1 person. So instead of 7,800,000,000, it's now 700,799,999,999 people. The idea is that that's pretty darn close to 12%. So that's why that assumption made sense. Okay, now let's actually take a look at an example of this one. And remember, we're going to do this in Minitab, so don't worry about that formula that I flashed earlier. Now, in this example, I just made that up, but it's pretty realistic. I made it up, but it's realistic. So, suppose the probability a company listed in NASDAQ, probability that the company will miss their forecasted earnings next quarter. That's like the coming quarter in June, not the quarter that we just wrapped up, is 20%. And let's say 20 companies are selected at random from NASDAQ listing. We want to find A through F. Probability of exactly 4 of the 20 will miss their forecasted earning. And then different probabilities between 6 to 8, fewer than 7, at least 4. In parts E and F, we want to find the expected value and the standard deviation. Okay. So, first of all, is this a binomial experiment, what we're about to do here? So it turns out that yes, it is, and I'm just going to go and justify all of those assumptions. First, what is our experiment here is selecting a company at random, right, from NASDAQ market. We have 30 trials. Each time you select one company, you are repeating that experiment. So there are 30 trials. That means repetition of the experiment. So we have n trials. The selection is at random, right? So the trials, that makes the trials are identical. Identical, that means however you conduct the experiment, you conduct it the same way as you move from subject to subject, or you move from item to item. Okay. Now, there are 3,300 companies, I believe, very close to it, or on or about that, right now listed in NASDAQ. So if I look at the ratio of, little n to cap n, N30 is definitely less than 0.5 times 3,300. 5% of 3,300, I believe that's 165. And 30 is less than 165. So that implies independence. So if I remove one company, don't put it back in there, that probability of missing the 20% probability is not going to change. Okay. And so that implies the independence of trials, so that fixed probability is sound, it's preserved. And probability success, actually success here is not beating, it was a miss. Okay, it's a missing. Success is missing the forecasted earning, because that's what I had up here, right? It's will miss their forecast 20%. So it's not beating but missing. Okay. Now each trial, by the way, here is Bernoulli. Any company that you select, they either will beat or they will not beat it. Okay. Or, I'm sorry, miss. They will either miss or they will not miss it. Okay. So probability of a miss is 20%. Now, here is the answer to the first 4 problems. You see, all of those, I got them from Minitab. The table is right to the right of that. So, in part A, probability of exactly 4. Well, exactly 4, that's right in here. Now, from here on, I'm going to annotate this table. So, according to each part A, B, C. So, I'm going to show you where that number came from. So, I look at 4, and looking at this gives you individual probabilities. Okay. That column gives you individual probabilities. So that probability is going to be 2053. Oh, actually probability of 4, sorry. I did it right. I see what confused me. Forget this column. That's just reference, the record number. So the probability of 4 is actually this probability right there. You see that? Because this is the random variable x. That's what that is. Okay, so x4, that's 2182. Okay, let me remove that one. Now, probability between 6 and 8 inclusive. So here's 6 and 8 inclusive. That means 6 or 7 or 8. So I added those probabilities. Now that I hope I did correctly when I added them on the calculator. Probability of less than 7. Well, less than 7, notice less than 7 here doesn't have equal sign. So less than 7 really means less than or equal 6, right? All right. And less than or equal to 6. So here's 6, right? Now because it's less than or equal, for less than or equal, you look at cumulative probabilities. Okay, that's what you look at. The cumulative probabilities. That means these. This is, remember, CDF, cumulative distribution function, less than or equal. So less than or equal 6, this is what I looked at. That looked at probability of 6 or 5 or 4, 3, 2, 1, 0. Your alternative is to do this, folks. You can individually add all of these numbers. See that? And that would equal to what's in front of it. Oh, less than or equal 6 again. Ah, I know. That's not 80, 40. I was looking at again 6 on the dark blackened column. It's a good thing I'm doing this together. Okay, so that's going to be actually 0.9133. 0.9133. Better than 91%. Okay. Now, in part D, probability of greater than or equal to 4. So let me remove these now. Probability of greater than or equal to 4. So let me actually mark this on my distribution. So here's 4. Greater than or equal means all of these, right? And actually, notice this is partial. This table is partial. It actually goes all the way down to 20 trials, right? So it's 9, 10, 11, 12, all the way to 20. So these numbers go on all the way down. So you got to actually do this. So if I want to use the distribution function, that means I got to add up a whole bunch of probabilities here, right? Well, I'm going to use the law of complement. I know the whole thing, right? What do I mean by whole thing? All of these probabilities, all of these add up to 1. So now let me tidy this up. Okay, so instead of actually adding all of these probabilities, right? Again, for greater than or equal 4 means I have to add up all of these probabilities all the way down to 20. Now it looks cleaner. Hopefully you can follow now. There. So instead of adding all these individual probabilities, we know the whole thing. I don't want to go in that column to confuse you, but this whole probability column 2, the total of column 2 is going to be 1. So I'm going to do 1 minus probability of x less than or equal to 3. And that probability of less than or equal to 3, this is an error. Probability of less than or equal to 3, that means I'm going to look at the cumulative distribution function, 3. Okay, and I'm going to calculate that probability this way. It's much easier. So it's going to be 0.4115. With probabilities, by the way, folks, we usually round to the nearest 10,000ths. Okay, I know Minitab doesn't, but that's what we do usually. Okay, so we have probability of less than or equal to 3. That's done. That's what that is. That's x less than or equal to 3. And then by subtraction, we're going to get the answer to this one. It's going to be 0.5885. So the probability is about almost 60%. that at least 4 of them will miss. Okay, so hopefully you followed this work that we did. Now, let's see. To do parts E and F, the expected value and the standard deviation, we have a formula for those. Minitab doesn't do that, but the formula is pretty easy to follow. So for this one, expected value of x is the mean of x, mu of x. That's going to be n times p, and I multiplied it, and the answer is going to be 4. So we expect 4 out of 20 companies to miss their earnings. Notice the expected value makes sense. If 20% probability of miss, then that's proportional. In a sample of size 20, you expect 20% of them, right, to miss. Now the standard deviation I calculated, that gives me 1.8. How do I interpret that? Well, I'm rounding it to about 2. So that means give or take 2. And with that give or take 2, that means anywhere from 2 to 6, right? Because I cannot have 1.8 of a company missing. So I'm going to go anywhere between 2 to 6 companies going to miss. And actually, here I got a probability here. Oops, sorry. This probability in here. So that's going to be 2 plus minus. That's going to be 2 to 6, I said. Now, where does this 86% probability of that come from? Well, I went back to the distribution table and I looked at between 2 to 8. There you go. The lion's share of probabilities are there. And if I calculate it correctly, there's about the 86% chance that that will happen. Okay. So, and there you go. We can say about 86% probability that anywhere from 2 to 6 will miss it. Just trying to use the standard deviation here. Okay, so now let's go to let's go to Minitab and actually do this in Minitab. Okay, now I do have a Minitab here, so there you go. So first we need to input the number of trials, right? Remember we had 20. So I'm just gonna label this column like we did before. We're gonna label this X. Okay, here's X. Next to that, this is binomial. I'm going to do probability of X equal little x. Next to that binomial, I'm going to do the cumulative distribution function. That means less than or equal little x. Okay, and there we have. So we labeled the columns. Now we need to calculate the probabilities, but let's actually type in the number of trials. I'm going to go 0. Make sure you put 0. Don't start with 1, right? Because 0 is a possible outcome. 0 means none of these 20 companies will miss. Okay. Now, to copy this down so you don't have to type him in, remember you highlight the column and you move the cursor until you see that plus. And you just go down as low as you want. I'm just going to stop at 20 because that was my number of trials. You can adjust the column width, by the way. If you go up here, you see the double-headed arrow. Drag it to the left. It changes the column width. And there you go. Now, let's calculate these probabilities. Probability distribution. So I'm going to go calc, probability distribution. We're going to go to binomial. Remember we were at geometric. Now we move to binomial. And then I'm going to go probability number of trials. That's going to be 20. Event probability, that for us that means probability of success, and that success was 20%. Now we do have an input column. Left click once, input column is X. You can left click once, select, or you can double click. Now don't okay, and these columns, see, we have them here. That's why you see them now appearing. Okay, what else? Optional storage. Where do you want to store these probabilities? Well, we want to store them in column 2, true. You can type it in, is what I did, or you can choose select, and don't worry about the other button, input constant. We don't want that. Okay. Oops, and that went in the wrong column. It went to C3. I see. No worries. Let me go actually calc probability binomial, and in this one I'm gonna go column 2. What happened? Calc probability distribution binomial 20.2. Oh, I see. Just because I was selected, and I'm gonna select the column 2. There you go. Now don't worry, I know that's repeated in column 3, but we're gonna overwrite these with CDF. So I'm gonna go calc probability binomial. This time deselect probability and select cumulative probabilities, and the optional storage. See, now we're going to go column 3, select, and it will overwrite those numbers. See, it did. And I'll show you, by the way, what the graph of this cumulative distribution function looks like. It's going to look pretty cool. Now notice, by the way, as we accumulate probabilities, as we look at total number of successes here, by the time we get to 20, look at this. See, the probability is 1, 1, 1, 1 almost, just because of rounding. So the CDF ultimately, because you're accumulating probabilities as you move across the values of random variable, as x gets bigger, bigger, bigger. So you're reaching the number of trials, number of successes match the number of trials. So that's why it becomes 1. So if you look at these numbers, see, they only get bigger, 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 bigger. We will actually do a graph of these in a moment, the graph of your cumulative distribution function. I didn't do that. Okay, so this is how I got those numbers. Now, let's say you want to do the distribution shape, graph, and probability distribution plot, view single, okay. And we're going to choose go up, slide. See, you can slide up and down. If you go up to binomial, number of trials was 20, the number of, or probability of success 20%, and hit OK. And there you go. The left click, double click, and that brings up the distribution. Notice how it's almost symmetric, huh? But it's somewhat skewed to the right. The smaller the p is, by the way, the more it's skewed to the right, because remember, p is probability of success. So for low success, right, probability of success low, you would expect fewer successes. So your bars are higher early on, and then they taper off. Means it's more unlikely to get higher successes. I'll show you this in a moment, what I mean. At p.5, the distribution will be perfectly symmetric, by the way. I'll do that also for you in a moment. Now, one thing, as I'm moving the cursor, you kind of see what's happening here. If I just don't move the cursor, I move my hand from the mouse. So if you just hold the mouse over, you don't have to click or anything. It actually gives you the parameter of the binomial distribution, n and p, and it gives you, that's at x equal 2. The probability of that outcome is 0.1369. So if you want to know what is probability of 8, just move over to 8. Probability of 8 successes, 0.22. Probability of no success, probability x is 0. Remember, x is the number of companies that will miss. But 0 means none of them will miss. Well, probability that none of those 20 companies miss their earnings is about 1%. So the other side of that coin is that means 99%, 99% that you have at least one miss. Okay. This is exactly one miss. I said at least one. That's 99, which means the sum of all of these probabilities. Okay, and let's see. Remember, you can annotate this graph however you like. So let me actually do this. I want to graph probability distribution. I'm going to do two distributions, and both of them binomial number of trials. I'm going to go 20 and 0.5. This is going to be the symmetric one, and then the other one I'm going to go scroll up, binomial number of trials 20, and probability of success I'm going to make it 0.87. so this is going to be left skewed, and check this out. And there you go. Sorry about that. I don't know what this Norton antivirus is. Okay, and this is what I was going to show you. You see how this is the one that has probability 0.87. Probability of success is high, and look at the number of successes, 15 to 20, very probable now. And there you go. So this is the one, and the one in blue is perfectly symmetric. Let me actually change that to just a binomial now, a single distribution within 20, probability of success 0.5. So you see how symmetric that is. You see that? Perfect symmetry. So with 0.5, that's always the case, regardless of the sample size. And if you throw in a distribution on top of that, it's going to be a normal distribution, that symmetric bell-shaped distribution that we looked at last week. Okay, so you can actually get the distribution plots. Let me delete this one, distribution plot. That one is the one for a problem. I'm going to delete this one. Okay. Oh, and what did I want to do? I was going to show you actually the graph of the CDF. The CDF, I'm going to go graph time series plot. Okay, this is just extra. Okay, this is not in your book, or I just want to show you what the cumulative distribution function looks like. So if I do a time plot, simple, okay, of I want to do for cumulative distribution functions, okay, and check this out. This is what it looks like. Isn't that cool? So notice the reason this rises is because we are accumulating probability as we go from 2 to 3, 4, 5, 6, 7, 8, 9, 10, all the way to 20. So this is what the cumulative distribution functions generally have that S shape to it. See? The letter S. That's what that is. Okay. And here it is. So that's what the cumulative distribution function is. And you can use this in different ways also. So if you hold the mouse over these dots, it gives you the cumulative distribution at that point. So probability of x less than or equal to 5 here is going to be 0.63. At this point, probability less than or equal to 8. The number on the far right is 8. That's going to be about 97%. Probability of less than or equal to 3. So that's what cumulative is. It's always less than or equal to. Okay. And there you have it. So we are actually done with the binomial distribution. Let me go back to my note. And let me check to make sure. Yeah, I'm good. So, time for another break, folks, right? Let's take a break from this good stuff. And while you're on break, I'm going to add more stuff. We only got one more distribution in section 3.5, and that is the Poisson distribution. And we'll be done with this week's lecture. So, let me pause, and you can actually pause and do something productive. Okay, so let's finish this off with our last of our discrete probability distributions. We're going to take a look at the Poisson probability distribution. Now, this distribution is named after the French mathematician Simeon Denis Poisson, who actually discovered this distribution about 3 years prior to his death. And he discovered this distribution while I believe he was working on distribution of time to disposal of criminal cases. So that's a little background about the distribution. But Poisson distribution is actually a very useful distribution, and the distribution often models the number of times that events occur in a given time interval. Okay, it's important to note that there are no number of trials like we had it in the binomial distribution. Okay, so instead we have a time interval inside of which these events could occur. The events would be the arrivals, for examples. Okay. Now, typically, the longer the time interval, the larger the probability of something happening. Okay. So, the distribution actually is a good model for rare events that are very unlikely to happen. And because of that, the distribution is called or known as the law of improbable events. That's the form of the formula for the distribution. That's what it's called. Now, in a Poisson distribution, again, we do have the assumption of independence here, but we assume that the intervals here are independent. Okay, the time intervals, if you will, are independent of each other. And the probability is proportional to the length of the interval. Okay, so again, proportional to length means the longer the length, the higher the probability. The shorter the length, the smaller the probability that something will occur. Now, these intervals are independent and mutually exclusive, so there's no overlap of the intervals. And again, the premise is that in a sufficiently short length of time in that interval, the events are Bernoulli. It means either something happens or it does not happen. Now, so what is a random variable? X here is the number of occurrences. Right in here is the number of occurrences of the event in the time interval of length t. Now, this is a Greek letter lambda, and here is a hint as far as how do we know we're working with a Poisson distribution. Usually you're given some kind of a rate. Again, notice we don't have a number of trials like we did with a binomial. So like you try to figure this out on your homework exam, what have you, or in general practice. With binomial distribution, you have a number of trials. With Poisson, you don't have trials. You have a rate of occurrence of an event. Okay, per unit of time. That unit of time could be every 30 minutes, every week, every day, every morning, every year, every 20 years, 30 years, what have you. Now, here's the form of the probability distribution. Now, a number of things in this formula. Lambda, of course, is the rate. E, which is the base of the natural log, is that irrational number, kind of like pi, except E is about 2.72. The denominator of the fraction is k factorial. And I'll show you on the calculator how to do this in an example that we do later on. So here I have some examples of a Poisson random variables. Check this out. All of these random variables follow a Poisson distribution. The first example is the number of times a tire blows on a commuter airplane per week. Again, this is not a likely event, right? Very rare. So this would be a good model for that. The next example is the number of patients arriving at an emergency room between 6 to 7 p.m. This could be on any given day, or a particular day if you have in mind, like on a Saturday, Sunday, Friday, whatever. Next is the number of phone calls received at the switchboard in 1 minute time interval. The number of earthquakes in a year. It could be the number of hurricanes, the number of typhoons, the number of pandemics in the next 40 years, the number of cars arriving at the drive-through window between 3 to 3:15 p.m. I actually have an example I've made up of that one for you. We'll look at that later. And finally, the number of people having a very rare blood disease. So all of these random variables follow a Poisson distribution. Now, the mean and the variance, interestingly, of a Poisson random variable is also the same as its rate, lambda. Okay, so for example, accidents occur at the rate of 5 per day at a given intersection. So how many accidents would you expect to see in a given day? It would be 5. The variance would be 5 also. And of course, the square root of that is whatever that is. That would be the number of accidents. Otherwise, the variance, remember, the units are squared. That would be accidents squared. So we usually look at the standard deviation. Standard deviation would be square root of the variance. Now here I have a note for you here. We can actually use Poisson. We're not going to do that here, but just something general information for you. A Poisson distribution is also used in approximating binomial probabilities, and in order to do that, it requires that the sample size is at least 100, and the product of n times p must be less than or equal to 10, which means n must be large and p small. Right? If n has to be at least 100, well, from the first inequality, right, from this one, when np must be less than or equal to 10, that means p must be less than or equal to 10%, right? So p must be small. And when these conditions are met, then here's how you can actually find the binomial probability using this formula. Okay. Now here I have like 3 examples we're going to go through, and on the third example we actually look at the distribution in Minitab, so on and so forth. So in our first example, let's say, suppose an accident occurs at a rate of 1 every 2 months. Notice how rare that incidence is. 1 every 2 months in a rural area. We want to find the probability that there will be no accident in a month. Now, got to be careful here, and I have highlighted this in yellow. Our rate is for every 2 months, but we want to know probability of no accident in 1 month, which is half that time interval, right? So we do need to adjust our rate. Our rate is 1 every 2 months, so that means 1/2 every month, doesn't it? And once we do the adjustment, then here's how we calculate the probability. So, first of all, the distribution of random variable x, it follows a Poisson. The symbol tilde means approximate. Actually, here it means it follows. So random variable x follows Poisson with the parameter lambda 1/2. So this would be the probability distribution from earlier, from what we had up here. Okay, where did my thing go? I guess I see what's going on here. Okay. This thing sometimes it just sticks and doesn't load things, but it's gonna come up anyway. The formula, there you go. It was updating, or actually probably was uploading to the cloud. That's why it was taking so long. So anyway, I use this formula down in here, and this is the Minitab output actually, which I'll show you how to get. Minitab gives me a Poisson with mean. Notice mean is lambda instead of rate. It calls it the mean because mean and lambda are the same. Mean 0.5 is 6065, and going through the formula I got 6065. Now let me show you real quick how you do these factorials and e to a power in case you want to do on your calculators also. So I'm actually going to go to my calculator and I'm going to do e to negative 0.5. So to do e to negative 0.5 second, Oh, actually, that's, sorry, didn't want to do that. E is this one. This is too tiny to see. There's E to negative 0.5. Enter. And there you go. 0.6065. What you're looking at is a TI-84 emulator that I have downloaded on my notebook. Okay. On my Surface Pro. So that's what that is. And you can also do factorials, by the way, folks. Let's say you want to do 10 factorials. You go to Math, and then you go right. You go to Prob, means probability. And then you can type 3. Actually, didn't want to do that. Sorry about that. Let me go again to Math. And then go 1, 2, 3, and then I'm going to down arrow to factorials. I can actually press number 4. I'll do it both ways. Okay, so that's how you can do this. So let me do 10 factorial. I'm going to go 10, Math, and then go to Prob, hit 4. And there's 10 factorial. Enter. Notice how large that is. It's about 3.6 million. That would be 10 by 9, 8, 5, 7, 4, 6, 3, 2, 1. Now remember, 0 factorial is 1 by definition. So I'm going to go 0 Math and then Prob 4. Ooh, I don't know what happened here. And try it again. 0 Math. And there you go. Factorial. There. Enter. And you get 1. You see that? Anyway, so that's how you can do factorials. And if you want to do e to a power, so let's say if you want to do e cubed. So I'm going to go second natural log and then type 3. That's e cubed. Okay. So that's how I got this from the calculator, and it matches pretty close to Minitab. In the second example I have here, let's say in this example, I have bank customers arrive at a rate of 3.2 every 4 minutes on a weekday afternoon. So here we have a random arrival situation, random arrivals that take place over a period of time. With this, you get into the topic of queuing theory, and Poisson distribution is used quite often as a model for queuing. Okay, and it's modeled for the arrival times in a queue. So in part A, I want to find probability that 5 customers will arrive in 4-minute time interval. Again, to the right, you can see the answer is 11%, right? 0.114 rounded. So I actually use my calculator again, which is pretty close to what Minitab gave me. Or again, a standard procedure. In part B, probability of x greater than 7 means what is probability that more than 7 people will show up in 4 minutes. Well, probability of more than 7 exclusive of 7, well, that puts it up to 8, 9, 10, and so on. So that's probability of greater or equal to 8. Now, in Minitab, the cumulative distribution function for all probability distributions give us less than or equal. Minitab doesn't give you greater than or equal to with the probability distribution. So, especially for discrete. Okay, so for this one, that means 8 or 9 or 10, 11, Remember, x goes to infinity in the case of geometric and in the case of Poisson. Now, to find probability of 8 or more, that's 1 minus probability of 7 or less. Because remember, the entire probability from 0 to infinity is 1. Because this is a probability distribution. So, and x less than or equal 7, I actually got this from the CDF, Cumulative Distribution Function, from Minitab. The mean is 3.2, which is right up here. and the probability 98.32. So I subtracted, and this is, hopefully I did it right. That's what I got. Almost 2% probability that you get more than 8 people in 4 minutes. Not very likely, unless it's a payday or something. Okay, in part C now, and this is a little tricky. Remember, our arrival rates were 3.2 customers every 4 minutes. We want to know what is probability of 10 customers every 8 minutes. So something I cannot do is this. I cannot, well, say 10, so that means 5 every 4 minutes. Okay, and adjust it for the fact that I have every 4 minutes here. We cannot adjust on X. Okay, and I'll explain why in a minute. I have a paragraph written for that. So we need to adjust the rate. Okay, remember, this is in an 8-minute interval. Our rate was for 3.2 for a 4-minute interval. So my lambda t, lambda is 3.2 times 2, that would be 6.4. Why times 2? Because this is 8 minutes. It's twice 4 minutes. Remember, up here we had 4 minutes. 8 minutes is twice that. So we're going to double up on our lambda. That means 6.4 every 8 minutes, because I have 3.2 in 4 minutes. Now, and here's the reason why you cannot adjust 10 in 8 minutes to 5 in 4 minutes. Okay. And then use that as your lambda. You cannot use lambda 5. So, and because these 10 arrivals in 8 minutes, they don't imply that there will be 5 arrivals in 4 minutes. Okay, there's no guarantees. And because we don't know the distribution of how these 10 arrivals are spread out over 8 minutes. Remember, our time interval is going to be very small. So we don't know the distribution of arrivals within a given time interval. We just know whether it's going to happen or not. Bernoulli. And so we always adjust lambda. You never adjust the X. And that's what I did. So probability of 10 in 8 minutes, that means lambda in 8 minutes, you would expect 6.4 customers. So I worked this one again on a calculator. I got 0528. Okay. And I don't believe I did not do that. No, I didn't do that in Minitab. But that's okay. You can try it if you like to. And I know I haven't gone to Minitab, right? I'll show you where I'm getting that stuff, and then you can try it. Let's take a look at example 3. And with this example, we will go to Minitab after we look at the answers. So in example 3, let's say for this one, we have cars that are arriving at a fast food drive-thru at a rate of 2.4 between 3 to 3:15 p.m. Now it's like, how can you have 2.4 of a car, right? Well, maybe that interval was bigger interval, right? Maybe it was in an hour interval and they shrank it to 15 minutes, and lambda turned out to be 2.4 adjusted. Okay. So here, if I let X be the number of such cars we want to find, and I'm doing using Minitab, we want to do parts A, B, C. Find probability of exactly 2 cars arriving between 3 and 3:15. Probability that at least 3 cars will arrive. Probability that no more than 4 cars will arrive between 3 and 3:15. So, using Poisson Distribution again in Minitab, exactly 2, that's exactly 2. Greater or equal 3, remember Minitab does less than or equal, so I go 1 minus. Greater or equal 3 means 1 minus less than or equal to 2. That means 2 or 1 or 0. And less than or equal to 2 is that. So that's 1 minus 5697, which this is how I got this number. Less than or equal 4, well, Minitab does less than or equal, so I got that directly from Minitab. All of these assume lambda is 2.4. Find the expected number of arrivals from 3 to 315. Expected is what the problem said, 2.4. And the standard deviation will be square root of that, 1.55 customers. Now, for this exercise, I have right in here, I have the histogram. Notice the distribution is indeed skewed. And I don't know what's happening here. There you go. I think the program is uploading to the cloud. That's why. So anyhow, this is the distribution of the arrival times. This time at that drive-through window. It is Poisson, and notice it's skewed to the right. Not quite symmetric. And here are, remember this part we did before for the binomial? Now I just added 2 columns to that. In my Minitab, I created a column for Poisson, individual probabilities, and then I did a column for cumulative probabilities. There you go. This is what the cumulative distribution function, by the way, looks like. So it's kind of like what we saw earlier. All distribution functions cumulative, they always rise and approach 1. See right in here, that's 1. And now let's go to, and I did black this thing out so it doesn't confuse me again. Okay, let's go to Minitab, and what we want to do is we want to create these 2 columns in Minitab, okay? And then get those probabilities that I have up here. Okay, let's get these numbers. So with that, I'm going to, this is Minitab, and let me X this out. Now, again, I've done a whole bunch of this stuff earlier on, just to insert it in my notebook, which I'm going to delete this, so I no longer have them. And delete, and delete. Okay, so these are all gone. Clean the slate, so to speak. And that's gone. Now, I'm also going to delete these 2 columns because we're going to create them ourselves from scratch. Delete cells. Okay, we're good. So let's actually create a Poisson distribution. So I'm going to label this as PO for Poisson. Right in here. Double click PO, and let me see why my this thing isn't responding. Okay, there, my keyboard wasn't fitting properly. So PO, and this is probability of x equal x. So this is actually the probability distribution function. If you want, you can space it out. And space this one out. Next one is going to be Poisson, probability of x less than or equal to little x. This is going to be our cumulative distribution function. And I'm going to stay with the 0, 1, 2, 3 all the way down to 20. Okay, so here's how you create the distribution function. We're going to go to calc like we did for binomial. We're going to go to calc here. And calc, probability distribution, and here's Poisson. See, I've already populated this thing, but let me delete these. Let me delete that. So you're going to get something that looks, there you go. It looks just like that, right? And input constant. Let me delete that. So it truly looks like what you have now. So we want to create probabilities. So click on probability, enter your mean. The mean was 2.4, right? And we're going to input columns. That means the x's are going to come from the column. When you click inside of that field, choose column 1. Double click. And optional storage, we're going to store these in column 4. Double click. And there you go. So when we say use columns, that means look up these numbers, plug these numbers into the formula and get the probabilities. So this is the probability distribution. And let's do the cumulative distribution. You go calc, probability distribution, Poisson. And this time I'm going to cumulative probabilities. And my input column for x's into the formula is going to be x. And we're going to place these in column 5. And there you go. So that's how I got those numbers. If you want to see what the probability distribution looks like, you go to graph, probability plot, view single, okay. And the distribution is Poisson. The mean is 2.4. Hit OK. And there you go. This is your Poisson distribution, the one that I had in my notebook. X this out. Okay, what else did we do? Let me see. Oh, okay, individual probabilities. Let's say probability of x equals 2. So for that, you go you go to calc, probability distribution, Poisson. You want probability. Now, you don't want input a column C, input a constant now. So this input a constant, actually, these are the x values. So I'm going to put 2. That means I want to find probability of x equal 2. And mean was 2.4, right? Okay. And there you go. So this is how I was getting those numbers. In exercise or example number 3, part B, we wanted probability of greater than or equal to 3. Well, for that one, I can go calc, probability, Poisson. Now, to do greater than or equal to 3, remember I did 1 minus less than or equal to 2. So I'm going to go cumulative if I want to do less than or equal. And 2 is good here. And this is how I got less than or equal to 2 to be that. And then 1 minus that gives me probability of greater than or equal to 3. To do less than or equal to 4, you go to calc, probability distribution, Poisson, and input a 4 here. And cumulative, make sure cumulative is checked. And this will give you probability of x less than or equal to 4 is 90%. So that's how I got all of those probabilities. Okay. And I think that's about it here, right? Boy, this was a very long lecture. So again, hopefully you can follow where these numbers came from. They're also in here, by the way, if you want to get them from here. So for instance, let me, since I have your attention, let me do this one. Let's say we want to do part, this one. We're going to do part A, okay? Probability of x equals to 2. That's going to be probability of x equals to 2 on the Poisson. That's this number, 2613. 2613 is what I have. Probability less than or equal to 2. Well, not all of that, but just this portion of it. Less than or equal to 2. Well, that's going to be right over here now, right? It's no longer that. It's the one next to it. It's this one, 5697. And that's where this was. Okay, so we got that one. And then probability of less than or equal 4. Again, I'm going to erase that. For less than or equal 4, well, this is 4. And that number is probability of x less than or equal 4. What this does, again, it adds up all of these numbers. Probability of less than or equal 4 means probability of 4 arrivals, or 3, or 2, or 1, or 0, which means none. Okay, so that's how you can also get these once you have the probability distribution. And now I can erase these. Okay, folks. Well, we are done with this week's lecture. So we covered 3 sections again. We are done with discrete probability distribution. So let me go back up, and wow, we covered a lot of grounds, huh? Okay, well, thank you for your attention, and please, if you need to, rewind the video and watch it, and hopefully everything will make sense, more sense the second time. Okay, with that, we are done with this week's lecture.